Okay, here's lecture 17. In this lecture we're going to be covering the Bloch equation, small tip angle excitation, and excitation k-space. So the Bloch equation is this equation that hopefully you've seen before that describes the motion of magnetization. Let me get the right color that I want to use here, 1 second. Describes the motion of magnetization. So some examples of this are the following. The first example is just when we stick the protons inside the main magnetic field, then we get polarization of the tissue, of the protons, or by the same mechanism we get equilibrium return to equilibrium after we haven't played out any type of pulse sequence for a while. The other example is excitation in the lab reference frame. Let's see the lab reference frame. So hopefully you've also seen the lab reference and rotating reference frames before. So here in this frame, we have not demodulated the rotation of the magnetization at the Larmor frequency, and so when we play out an RF pulse here, then that RF pulse causes as the RF pulse is tipping the magnetization down into the transverse plane, the magnetization rotates at at 3 Tesla would be at 128 megahertz, right? It's precessing around the main field, which is pointing along Z, and it's precessing at 128 megahertz, right? So then the frequency of precession is gamma times B0, right? And in this frame, often the RF, if you're playing out RF from a quadrature source, will also be rotating at 128 megahertz, or it will at least be oscillating. If you have a surface coil, with a linear polarization, it'll be oscillating along the x-axis here at 128 megahertz. Okay, and the final example I want to show you then is, oh, did not realize that would happen. Okay, the final example that I wanted to show you would be excitation in the rotating reference frame. I'll just write rotating ref frame for rotating reference frame. And so here we have B1 pointing along the x prime axis, and then we have the magnetization pointing initially along the z axis, which is really the same thing as the z prime axis here. Z prime is really the same thing as z, since demodulating only affects, or since shifting to the rotating reference frame only affects the x and y axes. And as we excite, we're knocking this magnetization down towards the transverse plane. Here's M. And in this frame, we've essentially demodulated the RF. This is essentially a demodulated frame so that the magnetization is no longer spinning around the z-axis. It's only spinning around the B1 axis. So effectively shifting from the lab reference frame to the rotating reference frame zeroes out the B field, or the Z component coming from the main magnetic field, right? We demodulate effectively the rotations of the magnetization due to the main magnetic field, and so then that becomes static, and also B1 then, if we're applying a constant pulse, will be or a pulse with a constant envelope will also just be static, pointing along x prime. So from here on out, we're going to be calling x prime and y prime just x and y. For brevity. And here is the Bloch equation, including relaxation. So we have 2 forms of relaxation here. We have relaxation due to T1, which controls the rate at which magnetization crawls back up towards MZ. And then we also have relaxation due to T2, which describes the decay, T2 here and here, which describes the decay of the MX and MY of the transverse magnetization. And then we have the gradients in here and the RF in here. So the RF could have a Y component and it can have an X component. Yeah, and that's it, I think, in there. So this guy is, as you might recognize, a first order differential equation. It's a relatively straightforward differential equation. And here, the G vector, I'm using this underbar here to denote a vector. Sometimes I use that little arrow vector up on top. Here G has three coordinates, x, gx, gy, and gz. These are all different gradient coils, different physical gradient coils inside the scanner, and we can usually control each of them independent of each other. And then R here I'm denoting as position. I've also previously denoted this as x with a vector. Here it's R and it's x, y, z, right? It's a vector that denotes position. Now, what we're going to do for the rest of this analysis, and indeed for pretty much the whole rest of this course, is we're going to ignore the relaxation terms here. And we can do this because excitation is fast compared to relaxation. So for the most part, we will be able to ignore T1 and T2. That's equivalent to setting T1 to infinity and T2 to infinity. Right? So that then this guy goes to 0 and these guys all go to 0. And here is the Bloch equation neglecting relaxation. You can see that the diagonal entries of the matrix here have gone to 0, and then we've lost the term off to the side there. And so now the magnetization will never change length, right? So this is actually then the solution to this equation then is a rotation. That is an operation that transforms the vector mx, my, mz, but does not change its length. Okay, so now we're going to get into a pretty central and important concept of this course, of the RF part of this course, and that is the small tip angle approximation. So this is very important to understand, so I'm going to present it a couple of different ways. So here's the situation. Under the small tip approximation, we are assuming that we have only a small deviation in flip angle that we're going to rotate the magnetization through away from the z-axis, right? So what we mean by small tip angle is we mean the angle with respect to the z-axis here. So before excitation, all the magnetization is pointing along z, and we're going to use the RF to rotate it a small angle away from z. Right? And it turns out that then if theta is small, then the mz component of the magnetization is approximately constant. Right? So we can say that mz is approximately m0, which is constant. Didn't give myself enough space to write there. Right? So it's a constant function of time. Right? So the first two equations of the Bloch equation decouple from the third. And that allows us to write the following. We get 0 plus gamma times g dot r times my minus gamma times b1y times m0. So here I'm just copying this first line out, but replacing mz with m0, giving us this term here. And then likewise the differential equation for my is minus gamma times g dot r, and then plus 0, just so you can see where the matrix elements are going. Sorry, this is times mx times mx plus 0 plus, let's see, plus gamma times b1 comma x times m0. Okay. So what we'll do here is we will combine these two equations, for the differential equations for mx and my, into a single equation by defining a complex valued magnetization magnetization, just as we did before for image reconstruction. Right? So before we were trying to reconstruct the complex number mxy, and so then that is defined as mx plus I times my. And this guy is going to be implicitly, though we've suppressed the dependence in our notation here, this guy is implicitly a function of both time and of space. Right? We are also going to define a complex RF. So then B1 will be equal to B1 comma x plus I times B1 comma y. And for now, this is going to be a function of time only. It won't become a function of space in time until we get to parallel transmit. Okay, so the differential equations for mx and my can then be combined just by multiplying the differential equation for my by I, that is equal to the square root of minus 1, again here, and then adding the two together. And so let's see what we get when we do that. Shift it down here, zoom in a bit. Okay, so this is equal to the following. It's equal to gamma times g dot r times my minus gamma times b1y times m0 minus I times gamma times g dot r times mx plus I times gamma times b1x times m0. Okay, so using our definitions for complex magnetization and RF, we can combine, let's see, we can combine this term and this term, and we can also combine the RF terms. We can combine this term and this term and get the following. We get minus I times gamma times g times dot r times mxy plus I times m0 times gamma times b1. So now what we have here really is a simple first order differential equation in one variable instead of two first order differential equations that are coupled. Okay, so now we're ready to develop an expression for the RF, for the total magnetization pattern excited by a pulse, and we're going to derive this in two ways. First, we're going to derive it graphically, which I think is a pretty intuitive way to do it, and then we'll derive it analytically, right? So we'll come to the same results, but we'll do it intuitively first, using a graphical derivation. Okay, so for the graphical derivation, let's say that we are given the following RF and gradient pair. Let's say we have this one-dimensional RF pulse that's real valued, and it's like a truncated sync waveform. And then we also have this gradient waveform, which is a refocused, half-refocused trapezoid. And let's say that we care about the final excited magnetization at the time t here. That's at the end of the entire pulse and gradient pair. And then let's also call our integrand for time, we'll call that tau. Right? So we're going to move along in tau here until we get to t, capital T, at the end of the pulse. Okay? Now let's look at just one little tiny increment in time, right? An increment delta tau in time. So a small increment in the RF then that comes from that small increment in time gives a small increment in excitation that's given by gamma times b1 of tau times delta tau. Okay, so then by the equation, by our first order differential equation then, if we plug in this into here, right, then we will get a small increment in mxy, which is given by delta mxy equals I times m0 times gamma b1 of tau times delta tau. Okay, so this little increment of time here, for example right there, gives a little bit of excitation, right? Brings a little bit of mz down into the transverse plane, and it couples into the differential equation like this. So then if we look at the little change in mxy over that discrete time period, then that will have mxy will have increased by that amount, right? And this is the amount exactly that it will increase by. And once that transverse magnetization is produced, it will precess due to the remaining gradient, right? It doesn't care about the preceding gradient because before now it was pointing along, remaining. Because up until the point at which it's excited, it's pointing along the z-axis, right? So it's parallel to the field, so it's not going to rotate around that field because we know by the Bloch equation that magnetization precesses in a plane transverse to that field. So if it's lying parallel to the field, it will not rotate, right? So once produced, that transverse magnetization produced by that one little delta step in time will precess due to the remaining gradient by an amount equal to this. So it's just going to be the integral until the end of the pulse of the gradient waveform times the position, right? So the gradient waveform is in Gauss per centimeter. Let me actually write this out, that might be helpful. So this guy is in Gauss per centimeter. Z, of course, is in centimeters then. And gamma, the gyromagnetic ratio, is in radians per Gauss. So then you can see that all these units here multiply out. So Gauss cancels with Gauss and centimeter cancels with centimeters. And we are left with radians, right? So this then we'll define as what we'll call kz of tau comma t times z. And this total guy is a phase, right? It has units of radians. It's a phase. It's an angle through which the magnetization will rotate at position z due to the gradient gz of s from the time that it is excited until the end of the pulse. Okay? So here we have to define kz of tau then. And really I should have written again here that this is also a function of capital T. So it's a function of the current time point and the point at which we're going to observe the final magnetization. And it's equal to minus gamma integral from tau to capital T of gz of s ds. Okay, so this is a very special guy right here. It is the excitation k-space trajectory for this gradient waveform. Okay, so that is the definition of excitation k-space trajectory. Okay, so it is the magnetization that we produced at this little delta step in time is going to precess by this amount, up here, right? And then at the end of time, it will have gained this phase. And so if we look at it at the end of the time, at the end of the pulse at time capital T, what we will have is I times m0 times b1 of tau times e to the I kz of t comma capital T. Sorry, that should be tau comma capital T. Oh, why would you do that? That's ridiculous. Okay. Okay, so e to the I k sub z of tau to capital T times z times delta, so delta times tau, right? So it's just multiplying that expression we showed on the previous page for the amount of magnetization produced by this step in time times the phase it's going to accrue up until the end of the pulse, and summing all of the bits up over the delta tau intervals. Now see, this weirdness happened here too. That's annoying. Okay, so summing up all the bits that we've excited over all the delta tau intervals and taking the limit, then we will get the following. We'll say that we're going to have, for each delta t, we'll have n time segments, and we will have I times gamma times m0 times b1 of I times delta tau times e to the I kz of, let's see, this is going to be I delta tau to capital T times z, and then we also need a delta tau down here, right? So we're going to have all those, and then n, of course, is going to go to infinity because n is equal to capital T over delta tau, which goes to infinity as delta tau goes to 0. So capital N here I'm saying is the total number of time segments in the pulse for a given step size delta tau. And this guy then, if you take the limit as delta tau goes to 0, you're going to get this following thing. You're going to get that the magnetization produced, at the end of time, which is capital T, and I should also change that. Actually, it holds for the little t as well, but whatever. So then at the end of time, that will be equal to the integral of the RF, and there should be only one gamma here, the I times m0 times gamma b1 of times the integral of gamma b1 of tau times e to the I kz of tau, comma t times z times d tau. That little tau got cut off by the scanner. Okay. So we have this following integral as the time steps, as the size of the time steps goes to 0. Okay, so here's this beast again. This is itself the small tip angle approximation. It says that at any given point in time, the transverse magnetization produced at a location R by a given pulse b1 of tau and a given k-space excitation k-space trajectory k is given by the integral of gamma b1 of tau times the Fourier kernel containing k, the dot product k and r, between k and r. Okay, so then you can see right away that this beast is a Fourier transform. And it actually looks an awful lot like the signal equation. So this is a very powerful result, right? So what is this a Fourier transform of? Specifically, it is a Fourier transform of the RF pulse itself. Okay? And it's evaluated along an excitation k-space trajectory k of tau comma t. So these are going to be the frequency locations along which the pulse is sampled, and then we integrate over all time, and each point in time corresponds to a k-space location, and then we get the Fourier transform of this guy, which gives mxy. Okay, so there's yet another sort of verbal way of thinking about this, intuitive way of thinking about this procedure. So what we can say is that we have an infinite pool of longitudinal magnetization, mz, from which we can draw mxy, and the procedure of drawing mxy is to excite it into the transverse plane. Okay? And then at each time point in the pulse, we knock down a little bit of fresh mxy from that mz pool. Right? So initially we have nothing, and then as we're moving along the time in the pulse, at each time point in the pulse we're knocking down a little bit of fresh mxy. Okay, so then once excited, each knockdown bit of mxy will now precess in the transverse plane, right, in the mxy plane, unaffected by the rest of the pulse in the other mxy, right? So that means that once we have this mxy in the transverse plane that we produced by this given time point it will not be rotated back out of the transverse plane or away from the transverse plane by the rest of the pulse, right? By any of the rest of the pulse or the other MXY. All right. And then at the end, we can then just add up all the MXY that are produced by the pulse to get the final excitation pattern. So the last thing that I wanted to do before I go through the analytic derivation of the small tip approximation is I wanted to tell you, point out the key difference between receive k-space trajectories that we've been working with up till now and excitation k-space. So receive k-space is defined as the area under the gradients from the time minus infinity, or really from the time at the once the magnetization is excited, because you can't accrue phase unless you've excited something, up to time t, right? So mathematically, this is commonly written as k of t for receive, Rx here, I'm saying stands for receive, is equal to the integral minus infinity to t g of s ds, right? Okay, and then so basically then, and this makes a lot of intuitive sense, right? You've got magnetization sitting there and it starts accruing phase due to the gradients, and so the total phase accrued is going to be proportional to the integral of all the gradients that it's seen. Now on the other hand, for excitation k-space, this is actually defined as the area under the gradients from the time t to the end of the pulse, right? So this is the fundamental difference, and it's really in the limits of integration of the gradient waveform that the difference lies. So ktx of t, so tx standing for transmit, is equal to integral from small t to capital T times g of s ds. Right? So capital T here again is the end of the pulse, or the time point at which we are going to observe all the excited transverse magnetization. And this is the expression for that, right? So the fundamental difference between the transmit and receive k-spaces are that transmit k-space is the integral of the gradient until from the current time point to the end of the pulse, whereas receive k-space is all the integral of all the gradient up to the current time t. And there's also this minus sign here, but actually there's also a minus sign in the receive signal equation in the complex exponential, but then we don't have another one here. That's sort of inconsequential. Alright, so now I will get to the analytic derivation of the small tip angle approximation.